So the filter that we are going to study, active filters that we are going to study are Butterworth, Lowpass and Highpass filter. So we are only discussing two types of filters, active filters, Highpass and Lowpass, and they are Butterworth filters. As you can see, the magnitude uh, the magnitude spectrum, or the magnitude response rather, of the Butterworth filter is given by this equation. So the frequency response of a filter, and frequency response is given by h of j omega or jf, as we studied, remember, in chapter number 1 when we were discussing Bode plots and stuff. So the frequency response of a filter is a complex number because it's a function of j omega, which is the complex frequency, right, on the complex plane. So it is a complex number. And a complex number has both magnitude and phase. So the magnitude response of a Butterworth filter transfer function is given by this, and observe this n over here. N is the order of the filter, and as I discussed with you, order represent how many capacitive elements in general you have in the circuit. That deals with the order of the differential equation of the circuit. Again, we are not going in the differential equation or anything. We're just gonna grab the standard model. As I said, we're gonna apply the frequency scaling, we are going to apply the impedance scaling, and then we will get our required filter. So basically this is our basic equation for the low pass active Butterworth filter. This is what we are going to use. In the decibel scale, in the logarithmic scale, we can represent this magnitude as 20 log 10 of m omega, and m omega is of course this. So we're gonna put this value, and this is our magnitude response in decibels. Fc is the cutoff frequency, and remember, as I discussed earlier, for the real filter, cutoff frequency is the one at which the magnitude of the filter goes to 70.7% or 0.7071 times the peak value. And for this, since the peak value is again 1, how do you find the peak value? You put f to be 0, that is a DC. When f is 0, then of course magnitude is 1 over 1, which is 1. So peak value of this is 1, although it is an active filter, but as I mentioned it to you, we are not providing any gain in the pass band, so peak value is still 1. That means the output of the filter maximally will be equal to the input of the filter, because when you write down the output equation, as I said, V out omega, magnitude of the output is equal to m omega, magnitude of the transfer function, times magnitude of the input, right? So at DC, at omega is equal to 0 or f is equal to 0, this is 1, so the output is equal to input at DC. And as you start increasing the frequency, denominator starts increasing, and m omega starts going down. So the peak value is going to be only at DC, and then it will start going down, and FC is going to be the cutoff frequency, like this. As you can, you will see soon all the waveforms that all the characteristic curve that I plotted using MATLAB. Alright, so this is the low pass filter, and for the actually first we're going to discuss we're discussing the high pass as well. For the high pass filter, it is the same transfer function, except what do you see here? This thing is inverse. So for the low pass is f over fc, and for high pass is fc over f, right? So that's the only difference between the low pass and high pass. F over fc is low pass, fc over f is high pass. So this is the magnitude of the transfer function of the high pass Butterworth active filter. Again, n is the order of the filter. Okay, now look at these curves. What are these curves? So these curves are given in the book as well, textbook as well, but you can easily draw this, and I will highly advise you to draw these. And how did I draw it? Basically, if you see on the x-axis, I have the normalized frequency. That is, this is either f over fc or for the low pass filter, or FC over F. So basically I replaced F over FC or FC over F by my X value. So I replaced in the equation, basically this is my 1 over square root of 1 plus x to the power 2n, right? And the same thing over here for the low pass filter, x to the power 2n. So whether you are looking at the low pass filter or high pass filter, so F over FC or FC over F is the normalized frequency, and I'm just calling it X. So I went ahead and I chose different values of n, that is the order of the filter, and I ran the value of x, from, let's see, I don't know, I used the scale as the logarithmic scale. So basically, I use in MATLAB, I use the semi-log x function when I'm drawing this curve, semi-log x, and then I'm going from, I don't know, 1 hertz to, I don't know, what is that, 10 to the power 5 or something, anyways, whatever you have. So I'm going from 1 hertz for x, and then whatever interval you want to take, 10, 100, whatever, and then I'm going up to, I don't know what I'm going up to, 10 to the power 5 or something, so 1 exponent 5, whatever I'm going up to, it doesn't matter, you can see the curve when you draw, comma, the equation that I have, right, the equation of m of w, which is 1 over square root of 1 plus x to the power 2n, right? So this is what I'm plotting, and you can calculate this, of course, before you put down this. So this is m omega, you can just put m over here, right, because you can calculate the values from this m, and for the range of x, so this is my x, you can calculate that for each value of n, right? So you can put a for loop if you want, for n is equal to 1 to 10. I think that's what I'm going from, 1 to 10, I believe. The first one is 1, I believe, and then the last one is 10. And then you can write down this equation, over here, m of whatever, if you're making a row vector, then n and all the column, basically like this, like we did in MATLAB course as well, and then write down this equation to calculate the values and assign those values for the specific value of n. So if n is equal to 1, it is going to assign it to the first row of the matrix M. When n is 2, it's going to calculate the value for 2 times 2, 4, and assign it to the second row of the matrix. So I calculated a matrix where each row of the matrix correspond to this equation for the specific value of n, which is the order of the filter. And then I went ahead, and all you have to do is semi-log x, and then whatever n, no, not n, sorry, the frequency f, or x rather, x comma m, and then it is going to plot all the curves for you. So make sure you have these curves, because if I ask you to design a filter, then you have to find the order of the filter, and to find the order of the filter, it is easiest way if you have these curves. So you can just move your mouse and you find the specific value to determine what order correspond to a specific value. Okay, so do this, and the same way you can you can plot the decibel values as well. Instead of the regular scale, you can plot the decibel values, what we calculated from this equation right here, this and this. Again, this is my normalized frequency, which I'm taking x. So that's how I plotted these two sets of curves, and we're going to be using these two sets of curves again, as I said, to determine the order of the filter for specific parameters. So let's look at this example. A low-pass Butterworth filter is desired to have the following frequency specification. Relative attenuation is less or equal to 3 decibel for the frequency less or equal to 800 Hz, and relative attenuation should be greater or equal to 23 decibel for f greater or equal to 2 kHz. So attenuation is the inverse of gain, that is, attenuation is 1 over gain, And in the logarithmic scale, attenuation, if you convert the gain into logarithmic scale, then attenuation is going to be come out to be negative of gain in decibel scale. In the regular scale, not the logarithmic, it is 1 over gain, and in the decibel scale, it's negative gain in decibel. So a gain of 10 decibel means attenuation of negative 10 decibel, and vice versa. If your gain is negative 10 decibel, that is, if your gain is less than 1, that means you have higher attenuation 10 decibel. So look at the first condition. Your relative attenuation is less or equal to 3 decibel for the frequencies less or equal to 800 hertz. Now 3 decibel has importance. 3 decibel means it's a cutoff frequency, because if you calculate the power associated with the signal, then the power at the cutoff frequency is negative 3 decibel if the peak value is 1. So that's why the cutoff frequency is also called 3 decibel frequency. So from the first piece of information, it is given to us that your 800 hertz it has to be less than or equal to 3 decibel for f less or equal to 800 hertz. So at 800 hertz it is 3 decibel, and less than 800 hertz it will be greater than 3 decibel, or sorry, less than 3 decibel. So attenuation, that means gain is greater than 3 decibel. So gain starts at 0, right, because the maximum value is 1, and if you take log of 1, that's going to be 0. So gain starts at 0, and then at the cutoff frequency it goes to negative 3 decibel, right? So when they are talking about attenuation, which is the opposite of gain, negative of gain, they are saying the positive 3 decibel is less or equal to positive 3 decibel for the frequencies of less or equal to 800 hertz. So this is the cutoff frequency they're given, 800 hertz. 800. So from this piece of information, you know that the cutoff frequency is 800 hertz. From the second piece of information, relative attenuation greater or equal to 23 decibel for f greater or equal to 2 kilohertz. So when you go here and you have, let's say, 2 kilohertz here, so they are saying that the relative attenuation is greater or equal to 23 decibel for f greater or equal to 2 kilohertz. That means at 2 kilohertz it is 23 decibel, and then as you go beyond 2 kilohertz, then it's going to start increasing. In other words, the gain at 2 kilohertz is negative 23 decibel, and as you go beyond 2 kilohertz, the gain starts dropping below negative 23 kilohertz. So basically this is your stop frequency that is given to you. FC is 800 hertz and f stop is 2 kilohertz, and in between that's the transition band right here, right? So you're going to take these two pieces of information, FC and f stop, and you're going to take the you are going to take f over fc, calculate f over fc, which is 2.5, because you're doing the low pass filter. So in the low pass filter, of course, you are doing 1 over 1 plus f over fc to the power 2n, right? So this is your magnitude response. So you first calculate f over xc, normalized frequency, from f is the stop band 2000, and fc of course is the cutoff frequency, which is given as 800 hertz. So you get 2.5. So now you have to determine what value, what order of the filter is going to satisfy this value of 2.5. So you are going to go ahead and look at this set of curves, and from this set of curves you're gonna go to the x-axis, and again if you have plotted them with MATLAB or Octave, then it's gonna be very easy, because when you're moving your mouse, it's gonna show you the value, changing value on the curve. So you're gonna go to 2.5 wherever 2.5 is, and then you're gonna start going up, and you're gonna start observing the y value. And when the y value becomes, for the stop band, becomes 23 decibel or more than that, not less than that, more than that, 23 decibel or negative 23 decibel, or so if you're talking about gain, then it's going to be negative 23 decibel or less. If you're talking about attenuation, it's 23 decibel or less or greater. So as I explained here, go to the decibel plot of Butterworth filter shown in figure 8.5. So right here, this is the decibel plot. So go to this figure, and so don't go on this one. Since we are talking about decibel, you have to go to 8.5, and then at 2.5 x-axis, move your mouse vertically over all of the curves, and wherever you see gain less or equal to negative 23 decibel, right? The first time you see, so you have 10 lines, right? So from the top, let's see at 2.5, you see that it is negative 2 decibel for n is equal to 1. So you're gonna reject this. Then the second one you see negative 15 decibel, you're gonna reject this. The third one you see negative 24 decibel. Now negative 24 decibel is less than negative 23 decibel. So you're gonna go ahead and say, okay, now this satisfies my requirement of the given frequency values. So you're gonna take that n is equal to 3 as the order of the filter that will satisfy your requirement. So and for n is equal to 3, as I said, when I did that, n is equal to 3 at x, f over fc is x, at x is equal to 2.5, it was negative 23.3 decibel. So it is easy to it is easy to miss it because it's very close to negative 23 decibel. It's very easy to go to 4, and 4 will definitely satisfy the requirement because it's going to be less than negative 23 decibel. But try to be as precise as possible, because again, there is no point of creating a higher order filter if the lower order filter can satisfy your requirement. So instead of going to the fourth one, which will definitely satisfy your requirement, but the filter is going to be more complex, if the third order filter satisfies your requirement, then you're just going to go with the third order filter. So you're going to choose third order filter from the given parameters. Another example, you have to determine the order of the filter for a high pass Butterworth filter. Gain is given negative 3 decibel, greater or equal to negative 3 decibel for f greater or equal to 2.5 kilohertz, and gain is given less or equal to negative 40 decibel for f greater or equal to 1.5 kilohertz. So remember, this is a high pass filter. So your filter is this, right? Filter is this. So this is still your cutoff frequency, right? 2.5 kilohertz. This is 2.5 kilohertz right here, and at that you have a gain of negative 3 decibel. And remember, it's eventually going to become 0 decibel, because eventually it's going to become 1 correspond to 0 decibel. So gain is greater or equal to negative 3 decibel, negative 3 decibel, negative 2 decibel, negative 1 decibel, and eventually 0 for the frequencies greater or equal to 2.5 kilohertz. So all these frequencies are greater than 2.5 kilohertz. And gain is less or equal to negative 40 decibel for frequencies greater or equal to 1.5 kilohertz. So over here, 1.5 kilohertz right here, the gain is 1.5 kilohertz. The gain is less or equal to negative 40 decibel, right? So this is negative 40 decibel or less than that. At that, I'm wondering, this should be less or equal to, I think this should be less or equal to, because you're going from 0 to 1.5 kilohertz as your stop band. So I'm assuming, I'm quite sure this is less or equal to, so I will modify that. So from 0 to 1.5 kilohertz, the gain will be negative 40 or less than that, right? So negative 40, we will assume that maximum gain is going to be negative 40 decibel at 1.5 kilohertz, or it can be less than that. Okay, so now you're gonna take these two values and you're gonna calculate first the normalized frequency, FC over F, because we are using high pass filter. So you're gonna choose FC over F. 2.5 is your cutoff frequency and 1.5 is your stop frequency. So you're gonna get 1.667. So again, you're gonna go to the figure 8.5 and you're gonna go along 1.667, and you're gonna go vertically, and whichever curve from the top, the first one, whichever curve from the top, the first one will satisfy the requirement of negative 40 decibels. You're gonna choose that as the order of the filter. So negative 40 decibel or less, remember, at 1.667, negative 40 decibel or less. So if it is negative 30 decibel, that is not gonna be the one that you're going to choose because it is higher than negative 40 decibel. But if it is negative 41, 42 decibels, then yes, it will satisfy the requirement. So according to my graph, when I moved my cursor along that, the 9th order filter satisfied the requirement. So the filter order for our high pass filter order for the given requirement will be 9. That means it's gonna be pretty complicated filter. We're not gonna design it, but in general, that's how you're gonna find it. So in the next, we're gonna discuss unity pole low pass Butterworth filters.